Windows Driver Framework. Components of a PCI driver. MapHardwareResources routine. MapHardwareResources is a routine that accepts three arguments. The first argument, which is a pointer to the FDO data structure. The second argument, resources raw, that is a handle to a list of the raw resources. The third argument, resources translated, that is a handle to a list of the translated resources. To make use of the MapHardwareResources routine, we need to perform these tasks. At first, we need to declare the descriptor variable. Then, we need to declare the I variable. Next, we need to declare the status variable. Then, we need to declare the bres port variable. Next, we need to declare the bres interrupt variable. Then, we need to declare the bres memory variable. Next, we need to declare the number of bars variable. Next, we need to ensure that the calling thread is running at an IRQL that is low enough to permit paging. Then, we need to open a loop that iterates over the count of the translated resources list. Next, we need to obtain a partial resource descriptor from the translated resources list by index, and store it in the descriptor variable. Then, we need to make sure that the partial resource descriptor is valid. Next, we need to open a switch over the type member of the descriptor variable. Then, we need to open a case that handles the port resource type. Next, we need to increment the number of bars variable by 1. Then, we need to make sure that the IO mapped CSR is mapped in the right order. Next, we need to initialize the members of the FDO data variable. Then, we need to initialize the bres port variable. Next, we need to close the case that handles the port resource type. Then, we need to open a case that handles the memory resource type. Next, we need to increment the number of bars variable by 1. Then, we need to check if number of bars equals 1 and perform the desired operations. Next, we need to check if the number of bars equals 2 and perform the desired operations. Then, we need to check if the number of bars equals 3 and perform the desired operations. If the number of bars is not recognized, we need to fail. Then, we need to close the case that handles the memory resource type. Next, we need to open a case that handles the interrupt resource type. Then, we will show an overview of the interrupt resource. Next, we need to close the case that handles the interrupt resource type. Next, we need to open a case that handles the unhandled resource types. Then, we need to close the case that handles the unhandled resource types. Next, we need to close the switch over the type member of the descriptor variable. Then, we need to close the loop that iterates over the count of the translated resources list. Next, we need to check that we got all the needed resources. Then, we need to call our own implementation of the read adapter info routine. Next, we need to call our own implementation of the self-test routine. Finally, we need to return the status. Task number 1, declare the descriptor variable. The descriptor variable is a pointer to the CM partial resource descriptor structure. The structure specifies one or more system hardware resources, of a single type, assigned to a device. Task number 2, declare the I variable. This variable will be used to index the translated resources. Task number 3, declare the status variable. In the code example, we declared the status variable and initialized it to status success. Task number 4, declare bres port variable. The bres port is a Boolean value that indicates whether the port resource was obtained or not. Initially set to false, to indicate that the port resource was not obtained yet. Task number 5, declare the bres interrupt variable. The bres interrupt variable is a Boolean value that indicates whether the interrupt resource was obtained or not. Initially set to false, to indicate that the interrupt resource was not obtained yet. Task number 6, declare the bres memory variable. The bres memory variable is a Boolean value that indicates whether the memory resource was obtained or not. Initially set to false, to indicate that the memory resource was not obtained yet. Task number 7, declare the number of bars variable. This variable will be used to count the number of base address registers for our device. It is initially set to 0. Task number 8, ensure that the calling thread is running at an IRQL that is low enough to permit paging. We simply use the paged code macro. Task number 9, open a loop that iterates over the count of the translated resources list. The WDF-CM resource list getCount method returns the number of resource descriptors that are contained in a specified resource list. We use the I variable to iterate over the count of the translated resources. Task number 10, obtain a partial resource descriptor from the translated resources list by index, and store it in the descriptor variable. We use the WDF-CM resource list getDescriptor method to obtain a descriptor of the resource by index. Task number 11, make sure the partial resource descriptor is valid. To make sure that the partial resource descriptor is valid, we simply check if it is not null. Task number 12, open a switch over the type member of the descriptor variable. In the code example, the developer performs a switch over the type member of the descriptor variable. Valid types are CM resource type port, CM resource type memory, CM resource type interrupt, and so on. Task number 13, open a case that handles the port resource type. The CM resource type port is used to handle a port resource. In this case, the developer needs to use the U.port member of the descriptor. Task number 14, increment the number of bars variable by 1. In the code example, the developer increments the number of bars variable to count only valid resources, and not the private device resources added by the PCI bus driver. The private device resources added by the PCI bus driver should not be touched by the driver developer. Task number 15, make sure the I/O mapped CSR is mapped in the right order. In this code example, the developer checks that the number of bars variable must equal 2, or fail otherwise. The order of the base address registers depend on the device itself, and may change from device to another. We will do an experiment with the serial PCI device under QEMU in the future. Task number 16, initialize the members of the FDO data variable. In this code, the developer converts the low part of the physical address of the port from unsigned long to void pointer. To perform the conversion, the developer used ulong to ptr inline function. The result is stored in the FDO data. In this code, the developer stores the port range, also known as the length, in the FDO data structure. In this code, the developer assigns the reading and writing routines in the FDO data structure. As you can see, to read data from the port, we use the read port ushort for example. To write data to the port, we use the write port ushort. There are functions for other data types as well, such as for byte. The mapped ports member is a Boolean variable that indicates whether the port is memory mapped or not. Task number 17, initialize the bres port variable. This is a Boolean variable that we set to true, to indicate that the port resource was obtained successfully. Task number 18, close the case that handles the port resource type. This is a simple task in which we simply break from the case. Task number 19, open a case that handles the memory resource types. The CM resource type memory is used to handle one or more memory resources provided by the device. In such a case, the developer needs to use U.memory member of the descriptor variable. Task number 20, increment the number of bars variable by 1. The developer increments the number of bars variable to count only the valid resources, and not the private device resources added by the PCI bus driver. The private device resources added by the PCI bus driver should not be touched by the developer of the driver. Task number 21, check if the number of bars equals 1 and perform the desired operations. In this code example, the developer knows that the length of bar 0 is 0x1000. He performs an assertion to make sure that he is talking with the correct device. The developer stores the physical address of the bar and maps the bar to virtual address space by using the local MapIO space routine. We will discuss virtual address space memory mapping in the future. Task number 22, check if the number of bars equals 2 and perform the desired operations. In this code example, the developer handles the bar 1. You can see that the developer handled the bar 1 2 times, in task 22 as memory mapped and in task 13 as port. The developer also fills the reading and writing routines here too. Task number 23, check if the number of bars equals 3 and perform the desired operations. In this code example, the developer knows that the bar 2 is used for flash memory. For the sake of simplicity, we will not go in the details of the flash memory. Task number 24, if the number of bars value is not recognized, we need to fail. In this code example, the developer returns an status value that indicates that an error has occurred. The loop reached an unrecognized bar, which may mean that the device is not the correct one. Task number 25, close the case that handles the memory resource type. We simply break from the case. Task number 26, open a case that handles the interrupt resource type. In this code example, the developer wants to handle an interrupt resource. Task number 27, overview of interrupt resource. In this code example, the developer initializes an interrupt config structure and creates an interrupt object for the device. For the sake of simplicity, we will not go into the details of the interrupt resource now. Task number 28, close the case that handles the interrupt resource type. We simply perform a break from the case. Task number 29, open a case that handles the unhandled resource types. In the code example, the developer used a default case to handle the unhandled resource types. The developer should not touch device private types added by the PCI bus driver. Task number 30, close the case that handles the unhandled resource types. In the code example, we simply use a break from the case. Task number 31, close the switch over the type member of the descriptor variable. In the code example, we simply close the switch. Task number 32, close the loop that iterates over the count of the translated resources list. In the code example, we simply close the for loop. Task number 33, check that we got all the needed resources. In this code example, the developer checks that all the needed resources were obtained successfully. Task number 34, call our own implementation of the read adapter info routine. In this code example, the developer calls his own implementation of the read adapter info routine. We will discuss the details of this routine in a future video. Task number 35, call our own implementation of the self-test routine. In this code example, the developer calls his own implementation of the self-test routine. We will discuss the details of this routine in a future video. Task number 36, return the status. We finally need to return the status. Summary. To perform the hardware resource mapping, the developer needs to obtain the base address registers of the target hardware device. For example, a hardware device may have multiple base address registers like bar 0, bar 1, bar 2, and so on. Every base address register has a corresponding resource type. For example, a bar may have a memory type, a port type, an interrupt type, and so on. To interact with the base address registers, we need to know the type. Once we know the type, we can use the corresponding routines to perform data exchange. For example, to read from a memory resource type, we may use MapIO memory to map the physical address of the bar to virtual address space, and then we can use the read register X function family or the write register X function family. For example, to read from a port resource type, we can use the read port X function family or the write port X function family, without needing to map the physical address. The best way to understand this is to interact with it. So, we will do a video in which we will demonstrate how to perform this interaction. The MapHardwareResources routine allows us to map the hardware resources for our hardware device.